Okay, well this video is going to cover what was version 1 of the polynomial test of Unit 2 Part 1. So let's go ahead and just get right to it. The first set we need to factor completely. The first step of factoring is to look for a common factor. I see that both of these are divisible by 2. So if I pull out that 2, I can see what's left. So that's going to leave x to the third power minus 27. Remember, when you pull out a common factor like this, you are dividing. Alright, so those 2's cancel. That gives me x to the third power. 54 divided by 2 is 27. Hopefully you will look at this and notice that this is the difference of two perfect cubes. 27 is a perfect cube because it is 3 to the third power. Now, I had encouraged you to take your calculator and create this list down the side of your paper or on scratch paper by doing 1 to the third power, 2 to the third power, 3 to the third power. Just in case you didn't have it memorized yet. And then you would notice that 27 is a perfect cube, so you're on your way. Once you realize that you have the difference of two perfect cubes, then you have to remember the pattern. Alright, so the pattern worked like this. First of all, we're going to keep that 2. Alright, so I'm just going to put that 2 out front, and that's going to stay there. Now focus on this part. Alright, this is the part that I'm doing now. The sum or difference of two cubes always factors as a binomial times a trinomial. Okay, that's a 2-piece times a 3-piece. The binomial is just the root of these two things. Okay, so if I take this and I take this, alright, x to the third power comes from x. I keep the same sign here. 27, as we mentioned, comes from 3 to the third power. So the root of 27 is 3, the cube root. Alright, so we've got that. Just for fun, I should go ahead and mention to you that if you wanted to avoid doing the whole making a list thing, your calculator will do the cube root. You know what, I'm not 100% you'll be allowed to use this calculator, but in case you are, and I hope you are, you can do the cube root by typing in the number 3 and then doing second and this button. That makes it the cube root of whatever you type in. So that's another way. That's another way of discovering that the cube root of 27 is 3, right? Or you could just do the list. Anyway, you've got your binomial. It came from these two. Now your trinomial. Your trinomial is going to have a beginning, a middle, and an end. The beginning comes from squaring this. So square this, you get x squared. Okay, the end comes from squaring this. Square this, you get positive 9. That's always positive. Now the middle comes from multiplying these two terms together. Alright, it's always going to be the opposite sign. So this is negative, so I know it's going to be positive. And then 3 times x is 3x. So that's it. Alright, that should be your answer to number 1. Let me clean this up a little bit. Okay, take a look at number 2. Again, the first step of factoring is look for a common factor. Alright, in this case, the greatest common factor is 2x squared. Both terms have at least 2 x's, so I will pull out 2x squared. And then I will see what's left on the inside. Again, to see what's going on the inside, I divide by the GCF. So I'm going to divide both of these by 2x squared. The 2's would cancel, alright, and that's just going to leave x. Alright, I'm going to have minus 8 divided by 2 is 4. the x squares would completely cancel out. So that's it. There's nothing else I can do with this. This isn't squared or anything, so I can't factor this any further. So this is actually the answer. So you know what, I'm just going to drag it over here. Okay, put it on the answer line. So boom, there you go. Let's move on to number 3. This, hopefully you recognize this as the difference of two perfect squares. So we're just going to immediately factor that with very little thought, using the pattern that we've memorized. Alright, when you've got the difference of two squares, it always splits right down the middle. So 9x squared is definitely going to be 3x and 3x. It's always going to be plus and minus, and again 4 splits right down the middle, so this is going to be 2y and 2y. Alright, so boom, that's it. There's nothing else I can do with that. So this again is the answer. So I'm just going to drag this over and put it on the line there. Okay, so that was the answer number 3. Okay, for the following quadratics, solve using the method indicated. Got to show your work. Alright, for this one we are supposed to complete the square. Alright, completing the square involves a very special number being right here, and this is not it. So we are going to add 8 to both sides. Alright, that's going to give us x squared plus 4x, leave a space, is equal to 8. Alright, because those canceled out. Now we're going to complete the square with that special number that comes from doing half of the middle squared. Half of 4 is 2. 2 squared is 4. Okay, so I'll do plus 4. If I add 4 on the left, I've got to add it on the right. So this will always factor now as the same thing twice. Okay, so x squared, that'll be x times x. 4 will be 2 times 2. Alright, plus and plus. And of course this is 12. The benefit of having the same thing twice is that I can now write this as x plus 2 squared equals 12. Alright, now because I have something squared, I can unsquare it by doing the square root. Don't forget the solution will be plus or minus. Anytime you take the square root of both sides, you've got to put a plus or minus. Okay, so let's move this over. So the radical will unsquare this, so then I will have x plus 2 equals plus or minus. Now the square root of 12 is going to be 2 root 3. Okay, but this is what you might see, alright, 2 root 3. Whoops, wrong thing. Okay, so instead of plus or minus radical 12, we have plus or minus 2 root 3. Now we need to just subtract 2 from both sides, being careful to put it in front. And that really is going to be our final answer, so I'm going to go ahead and put it here. X equals, x equals negative 2 plus or minus 2 root 3. Okay, number 5. This one we are supposed to solve by factoring. Okay, so let's factor this. Yeah, so 2x squared, we look at that first. That will only factor as 2x and x, so done deal. Looking at the 35, 35 can only be 5, well, okay, it could be 5 times 7, or technically it could be 1 times 35. But, you know, most likely it's going to be the 5 and the 7. Now, it might be 5, 7, or it could be 7, 5. The way we know which one it is we check the whole the inner plus the outer has to equal the middle. So inner, I have 5x. Outer, and I'm multiplying here, I have 14x. I'm trying to get a 3 out of this, and all I can control are the signs. There's no way I'm going to get a 3x out of 5x and 14x. So this is not working. So maybe it's the other way around. So let's try 7 and 5. Okay, in that case, inner I have 7x, outer I have 10x. And again, I'm trying to get positive 3. I can do that. If I have a negative 7 and a positive 10, that would make a positive 3 answer. Okay, so that means negative 7 is right there, and the positive 10 would come from this being positive because we're talking outer. One last thing I have to check. Does negative 7 times positive 5 give me negative 35? Yes, negative times a positive is negative. So there I've factored it. Okay, once you have it factored, you don't stop because this is an equation and we are supposed to be solving, alright? The directions say solve. Solve means find what x is. Alright, if we were just supposed to factor and stop, the directions would just say factor like this, where it says factor completely. Notice up here we just factored and stopped. Factor completely. But down here we are solving. These are equations, so we keep going. The way we keep going is by setting these factors equal to 0 and solving. So we're going to be doing 2x minus 7 equals 0, and we're going to be doing x plus 5 equals 0. On this end, if I add 7 to both sides, I get 2x equals negative 7. If I then divide both sides by 2, like so, then I get x is equal to negative 7 over 2. So that is one answer. Meanwhile, I will subtract 5 from both sides. So that will give me x equals negative 5. So these are the two solutions. So negative 7 over 2 or negative 5. Okay. Now, number 6, we're supposed to factor using the quadratic formula. Alright, let us remember that the quadratic formula says if we have an equation that's in the form, let's see, ax squared plus bx plus c equals 0, then we could find the solution by doing this: opposite of b plus or minus square root b squared minus 4ac all over 2a. And you had to memorize this. It helped to know the song. Opposite of b plus or minus square root b squared minus 4ac b squared minus 4ac all over 2a, all over 2a. Yeah, learn the song. What? Don't mock me. Don't hate, don't judge. Anyway, this is the quadratic formula, and that's what we're supposed to be using for this problem. Now, this is not quite in standard form. Alright, for standard form, we need everything on the left except for equals 0 on the right. So basically, this negative 5 needs to get to the left. Yeah, get. Yeah, arrow. So we're going to accomplish that by adding 5 to both sides. So this is going to become 2x squared minus 8x plus 5, you see, equals 0. Okay, that means that a is 2, b is negative 8, and c is 5 in terms of plugging into our quadratic formula. Now, whenever you do the quadratic formula, I want you to calculate the discriminant separately. Oh, you forgot what the discriminant was. Is that what I hear you saying? Well, the discriminant is this part in here. Okay, all of this. That's the discriminant. You know, it probably would have been easier to do something like this. Bam. Alright, now that would temporarily block it out. But, you know, anyway, you get it. B squared minus 4ac. Do that part first. That's a discriminant. So, I think I'm going to do this in a different color. So our discriminant, you know, our b squared minus 4ac is, so that's negative 8 squared minus 4 times 2 times 5. So let's see what that is. Alright, negative 8 squared, that's positive 64. And I encourage you to type positive 64 instead of trying to write negative 8 squared down. Just do that part in your head. So there's my b squared minus 4ac. Okay, so that is 24. So our discriminant is 24. Always calculate that first. Now we can go on with the rest of the problem. Okay, so according to the quadratic formula, we need opposite of b plus or minus square root. So opposite of b is negative 8, so the opposite of b is going to be positive 8 plus or minus square root. Now the discriminant goes onto the square root all over 2a. Well, a is 2, so 2a is 4. So boom, this is where we should be starting out. Do not type this whole thing into your calculator. The only thing that you should be putting in your calculator is the square root of 24. And that's if you can't do it in your head, like I can. Alright, no time to teach you that right now. So, square root of 24 is 2 radical 6. Alright, so then this becomes x equals 8 plus or minus 2 root 6 over 4. Now this is essentially the answer, except for you should always look to see if you can reduce these three numbers. Now it's got to be all three or nothing. Now one of my students tells me that, well, I say one of my students, but one of the students who I help, who is actually somebody else's student, says that her teacher has them put a heart around these three to remind them that it's all about these three numbers. The radical 6 has nothing to do with it, and it's all or nothing. If there's a common number that you can divide all three of these by, do it. If it's just 2 of them and not the third, forget it. All of these are divisible by 2, so we should do that. We must do that. Okay, so we'll divide the heart by 2. I like the heart thing. And once we do that, that should be the final answer. So I'm going to move into position over here to put my final answer down. So that 8 I'm dividing by 2, so I'm going to have 4 plus or minus. Now these 2's sort of cancel out. 2 divided by 2 is 1. So I'm just going to put radical 6. And 4 divided by 2 is 2. So there you go. That's your final answer. Okay, please understand this is really 2 solutions. This is really, I think I'll do this in gray. This really means 4 plus radical 6 divided by 2, or 4 minus radical 6 divided by 2. That's what it really means, but you can leave it like the blue. Okay, let's take a look at number 7. Solve and graph, solve the inequality and graph the solution on a number line. Okay, inequality. C is greater than or equal to 0. The best thing to do is to solve this using factoring. Alright, so in fact for a minute I'm going to ignore the fact that this is actually an inequality, and I'm going to factor it and set it equal to 0. That way I'm getting the x-intercepts. So x squared is going to be x times x. 12, alright, slow down. 12 is either going to be 3 times 4, or 2 times 6, or 1 times 12. Alright, I'm just going to go in that order. So, well, no, I'm not. I'm going to look at the 4. Because there's no number in the front, you know, the leading coefficient is 1. I can immediately look at these and look for the one that could give me 4. So 2 and 6. Okay, I need a positive 4. So a negative 2 and a positive 6 will give me a positive 4. So boom, there you go. Now, to get the x-intercepts, I would set these equal to 0. So x minus 2 equals 0. And x plus 6 equals 0. Adding 2 to both sides gives me x equals 2. Subtracting 6 from both sides gives me x equals negative 6. Okay, so what I have here are the x-intercepts. 2 and negative 6. I'm going to go ahead and put those two on my number line. So really the negative 6 goes over here, and the 2 goes over here. Alright, boom, number line. Now, in reality, we're trying to find out where the function is greater than or equal to 0. So what we're going to have to do is pick some test values, one in each one of these zones. Alright, we have a zone over here, a zone in the middle, and a zone on the right. So you can pick any number you want. Now in this zone, let's see, I've got negative 6, so I could pick negative 7, negative 8, negative 9, anything like that, anything in this area. I think I'll go ahead and pick negative 8. Okay, will be my test value there. Now in here, I love to pick 0 for a test value because it makes the calculations easier. And 0 is definitely between negative 6 and positive 2. Let's see, now over here, I could pick I could pick 3 or 4 or 5. You know, anything, I could pick 100. But I'm going to go ahead and pick 4. So you pick whichever values you want to test, but you're going to need one in each zone. Now, I like to stay organized, sort of like this. I make a little table for myself. Okay, and you know what, maybe I'll just even do it just like this. Okay, so in this area I will calculate with negative 8, and here I'll do 0, and over here I will do the 4. So let's see, now remember, what I'm dealing with is this x minus 2 and x plus 6. Okay, so I'm dealing with, let's do the negative 8 first. Alright, so what I want to see is, if I put in negative 8, I want to see if it makes a true statement. And I'm shooting for this to be greater than or equal to 0. Okay, so if I put in negative 8 for the x's, that makes this negative 8 minus 2 and negative 8 plus 6. Alright, I'm just putting in negative 8 here and here. Alright, but it's got to be, I'm looking to see if the value is greater than or equal to 0, just like this. In fact, maybe I'll just change this back. Greater than or equal to 0. Okay, so is it yes or no? So let's keep going. So negative 8 minus 2, that's negative 10. And negative 8 plus 6, that is negative 2. Okay, so I'm trying to find out, is that greater than or equal to 0? Well, a negative times a negative is a positive, so in the end I get 20. Is that greater than or equal to 0? Well, yes. Yes, it is. Okay, alright, I'm going to come back to that. But for now, I know that with negative 8, I get a true statement. So that tells me that this zone is going to be a zone of solutions. Now, what about the middle zone? If I put in 0 instead, then I get this, 0 minus 2. I'm just putting 0 where the negative 8 was. And I'm going to get 0 plus 6. And I'm trying to see, is that greater than or equal to 0? Well, that's going to give me negative 2 and 6. Is that greater than or equal to 0? Well, that's going to give me negative 12, right? Is that greater than or equal to 0? Question mark. Answer, no. That's a negative value. Negative numbers are not greater than 0. They're less than 0. So that's a no. Okay, finally we will test the 4 out. So if I put the 4 in there, it's going to look like this. 4 minus 2 and 4 plus 6. Trying to see, is that greater than or equal to 0? Well, that's going to give me 2 and 10. And you can already see that this is going to be greater than 0. That's going to give me 20 greater than or equal to 0. Just like before. Look at that. So that's, again, definitely a yes. So our test values tell us the places where we got a true statement, where you see these yeses, that's where the solutions are. So that tells us we will have solutions in the first area and the third part of the graph, but not in the middle. Now let's talk about the points themselves, the x-intercepts themselves. Let's talk about negative 6 and 2. Well, in this case, we were looking for values that were greater than or equal to 0. Equal to 0 is fine. And these values themselves are the x-intercepts. They are designed to give us a value that is equal to 0. So we will include these in the solution set. The fact that it's or equal to is a big hint that this is going to be a closed circle. So we'll have closed circles at the x-intercepts, and we will draw arrows like this to show that we have solutions here and we have solutions here. And we'll just leave this empty to show that we don't have solutions in this area. That was a no. Alright, so there's your graph. Now, you know what, maybe I'll move these down here, because unless you're watching the video, it looks like this is part of the number line, and it really isn't. Okay, can I erase? Okay, so there is the graph of the solution. Now, the solutions themselves, we will go ahead and use interval notation. To capture this part of it, this starting from the end, this is negative infinity. So we have negative infinity and then all the way up to 6. And we will use a closed bracket to show that we're including this endpoint. And then we'll have to put a union because we have these two separate pieces. And then we will say starting with the 2 and include that 2, and it goes all the way to positive infinity. Okay, this is the solution and this is the graph. Okay. Alright, let's talk about this graph. Now, please understand that the idea is that this goes forever in this direction. Okay, and this also continues forever like so. It doesn't stop. It just runs off the graph. Now with that in mind, the domain is the x values of a function, alright? All the input values, the x values. So graphically, it's how far to the left and right it goes, left to right. But since this graph goes left and right forever, we will say that the domain is negative infinity to positive infinity. Okay, now the range. The range is the y values of a function. So in this case, graphically we're talking about how low it goes to how high it goes. Now, the bottom of this graph, the lowest point is here. Now, we're going to need these decimals to help us know exactly how low that is. Which one of these numbers is telling me how low this is? It's this number right here. Okay, the y value is telling me the height. Alright, the x value is telling me how far over I am, and that's not what I need right now. So I'm looking at that negative 6.25. That's how low it goes. And then how high it goes, well, it goes forever. So the range is going to go from negative 6.25 to infinity, bottom to top. It has to be in that order. Okay, so negative 6.25 to infinity. Alright, and we will include the negative 6.25 with a bracket. Now, end behavior. Alright, in words, end behavior is all about what's happening on the left side of the graph and what's happening on the right side of the graph, looking at the ends, right? That's why they call it end behavior. So in words, we would say it like this. We'd say on the left, and the idea is, does it rise or fall? Alright, well on the left it rises, alright, it's going up. What about on the right? Well on the right it also rises, alright, it's pointing up on both sides. So on the left it rises, and on the right it rises. Okay, so it's just a matter of turning that into math symbols. Okay, now the way we say on the left is we say as x approaches negative infinity, and that makes sense, doesn't it? Because negative infinity is over here, it's on the left. Okay, so as x approaches negative infinity, that means we're heading to the left. So then what happens as x approaches negative infinity? Okay, and we say f of x approaches. Alright, so far everything I've written, that part never changes. Okay, this means on the left, the function, and it either rises or falls, or occasionally there's an asymptote, but that's another, we'll talk about that another time. Well, it rises, alright, the function goes up and up and up. So how do we show that? We say it approaches positive infinity. So this is a symbolic way of saying on the left, the function rises. As x approaches negative infinity, the function approaches positive infinity. Now, I want to say on the right, it falls. Okay, well if this is the left, okay, this is how you say on the right. You say as x approaches positive infinity, and again you say what happens to the function. Alright, if it rises, we say positive infinity. If it falls, we say negative infinity. Alright, we already saw that on the right it rises, so we will again put positive infinity. Okay, on the left it rises, positive infinity. On the right it rises, positive infinity. Alright, that's how you do end behavior. Okay, in most cases that we're dealing with at this point, all of this is going to stay the same. It's just if it rises, it'll be positive infinity, and if it falls, you'll put a negative infinity. Anyway, the x-intercepts. When we talk about x-intercepts and y-intercepts, we are talking about points, ordered pairs. The x-intercepts are the points where the graph touches the x-axis. Let's see. There are 1, 2, 3, 4 x-intercepts. Alright, x-intercepts are always something comma 0. So what we have, this one right here is -8 comma 0. And then this one here is, what's that, -5 comma 0. And this one is 1 comma 0. And this one is 8 comma 0. Those are the 4 x-intercepts, the 4 spots where the graph touches the x-axis. So I'm just going to recopy what I just said. Alright, and again, an x-intercept is an ordered pair, so don't just put a number, put the whole thing, including the parentheses and the comma 0 and everything. Okay, now the y-intercept, and yeah, there's only one of them for this problem. The y-intercept is going to be, let's see, I think I'll do it in green. The y-intercept is right here. Now, to me, this looks like a decimal. It seems to be a little bit above 1. So, you know, it's something like maybe 1.3 comma 0. I'm estimating, and you know, I would give you anything between 1 and 1.5. Alright, so the y-intercept is approximately 0 comma 1.3. Whoa, I messed up the order when I wrote it down, didn't I? Yeah, yeah. A little embarrassing. Okay, yeah, it's on the y-axis, so we're talking 0 comma 1.3. Get it right, Burton, get it right. Anyway, moving on. Maximum and minimum. Now, when we talk about maximum and minimum, we are only talking about y values. These will not be ordered pairs. Okay, these are y values we're looking for. So the maximum value, well, there is no maximum value. Alright, this graph goes up and up forever. So there is no maximum value. So we just need to say that. Alright, no max. But there is a minimum value. Alright, remember, we're looking for a y value. Alright, remember here when we were doing the range? Well, this is the minimum value. Right there, it's that y value, -6.25. Now, when we talk about where the maximum is located, well, okay, fine, there was no max, so you can't tell me where it's located. But when we talk about where, now we're talking about x values. Alright, yeah, maybe I'll make little side notes here. This is a y value. Okay, but this is going to be an x value. Okay, so where is the minimum located? So this is the location. Alright, 5.5. Alright, so if I ask you where, I'm asking for an x value. If I ask you what, I'm asking for a y value. Alright, moving on. Intervals of increasing and intervals of decreasing. Alright, well, I might have to erase some of these points. Alright, let me clean up the graph. Okay. Let me color coordinate this entire thing. Imagine that you're on a journey traveling from left to right along this graph. Sorry, I'm going to need a thicker pen for this. I'm traveling from left to right. For part of the journey, you're going downhill, and then you're going uphill, and then you're going downhill, and then you're going uphill. Everywhere you're going downhill is a decreasing interval. Anytime you're going uphill is increasing. So I'm going to color all the downhill parts red, and I'm going to color all the uphill parts green. Alright, so, and you have to be traveling from left to right. Okay? So, as I go from left to right, I'm going to be going downhill from here. Wow, that is loud. What you're hearing is the emergency alert from my iPhone. Flash flood warning. This area till 3:15 a.m. Avoid flood areas. Check local media. Alright, I don't think I'm in a low-lying area, but it's good to know that my iPhone has my back. Alright, so it's going to be a decreasing interval from there to there. I don't like this color green. It bothers me. I'm going to use this color green. Alright, so it bottoms out right here, and then it starts going uphill. So it goes uphill from here to here. Okay, and then it goes downhill again. So then it's going downhill from here to here. Alright, and then right about there it switches, and then you start going uphill again. Okay, so these are the decreasing intervals that you see here in red, and the increasing intervals you see here in green. Now, when we talk about these intervals, though, what we are talking about are the x values. Alright, so just concentrate on the x values. Okay? So, x value wise, see where the increasing interval. So look at the green intervals. Alright, so let's start with this one. But just give me the x values. Let's see. Alright, so x value wise, this interval goes from here to here. Okay, so it goes from -7 to -2. Alright, from here to here is this first green interval. So -7 to -2. Only the x values. Alright, my pen is too thick now. Calm down, pen. Okay, increasing interval. So from -7. You know what? I should use round. Alright, we shouldn't include the -7 itself, because right at the point where it changes, it's actually 0. It's actually no slope. It's neither increasing nor decreasing right at the borderline. So we won't include the -7. But everything between -7 and -2 is increasing. It's all green. Okay, and then the other green interval is from here. Well, it starts off, well, and you know what, I'm messing that up a little bit. This is 5.5, so it's here, 5.5. But look, this one doesn't end. It keeps going forever if I kept going that way. Alright, so it's going to start at 5.5, but it actually continues to the right infinity. Alright, it goes forever that way. So, okay, so, well, you know, I guess I don't have to say union. I think I can just list. So, I will say 5.5 to infinity. Okay? And I know this looks like an ordered pair, but in this context, it's understood to mean all the points between, all the x values between -7 and -2. So those are the increasing intervals. Now the decreasing intervals are the red ones. Alright? Now this goes forever to the left, this red guy. So it starts off at -infinity. Okay? A decreasing interval. So this first one begins at -infinity. And it ends right here at an x value of -7. So it goes from -infinity to -7. Okay? And then the next one begins at -2. So it goes from -2 to 5.5. Okay, x value wise. It goes from -2 to 5.5. It goes from here to here. So I will put -2 to 5.5. Alright, so those are my decreasing and increasing intervals. That's how you do that. Okay. Does this graph represent an even, odd, or neither function? Explain why. Well, it will be an even function if it is symmetric around the y-axis. Okay? In other words, if I were to look at the y-axis, does it form a line of symmetry? Okay? And I'm going to say no to that. Alright? Just highlighting the y-axis here for a minute. Okay, there's my y-axis here in red. If I were to fold this graph along this y-axis, these are not mirror images. Alright? This side's going up, this side's going down. You know, there's something going on here, but it's not using the y-axis as a mirror. So it's definitely not even. So it's either odd or neither. Now the way we recognize odd symmetry is if it's going to be odd, then it should be symmetric around the origin. Okay? And what that means is, if I were to take this graph and rotate it and turn it in a circle upside down, the graph should still look the same. Now I can kind of sort of do that, not perfectly. Using Microsoft Word, I may have to do a couple adjustments, but you see me like here. So far I've rotated it sideways. I'm going to keep rotating until it's upside down. Okay, so the question is, does it still look the same? If it does, then that would be odd. It would be an odd graph because it has a rotational symmetry around the origin. And you know, one way that would help me just illustrate this, well, I didn't really mean to color that border red. If I were to trace this graph, and it's difficult with an electronic pen, but I should be able to do it well enough to give you the idea. If I were to trace this graph, okay, so that when I rotate it back again, you will be able to see whether or not it matches. Okay, again, not a perfect tracing job, but enough to give you the idea. So if I take this and rotate it, let's see if it matches still. So I'm going to take this and rotate it. See there, it's sideways so far. Rotate it all the way. Bam! So you should be able to see that even as I rotate the graph upside down, it matches. It looks the same upside down using the origin as a center point of rotation. So that shows that this is in fact odd. This is an odd function. So as far as our explanation, we will just say something like this. This is an odd function because it has rotational symmetry around the origin. Alright, boom, there it is. Feel like coloring this a color. Alright, let's move on. That's all there is to that. Alright, number 10. Sketch a graph on the coordinate plane that has the following characteristics. Alright, we need something that has a range negative infinity to positive infinity. So we need something that goes up and down forever. We need something that has n behavior. Let's see. This is saying on the left it rises. Okay, maybe I'll just put some words to that. I missed my target. So this is saying on the left it rises. So I need something that's on the left, it's going up high. And this is saying on the right it falls. Okay, so I need something that rises on the left and falls on the right, and you know, and that will help me with the range because it's going to go up forever and down forever. What else? And it needs to be an odd function. Well, we just talked about that. We talked about the fact that it needs to have symmetry, rotational symmetry around the origin here. Okay, so we need something that has rotational symmetry so that if we spun the graph around, it would look the same. Okay, so we can do that. So let's start by making sure it goes through the origin. That'll make our lives easier. So every point I pick, if I draw a diagonal line through the origin, I'm going to include the point on the other side of the origin. So there's one point, there's another point. Okay. So let's keep going. Alright, so I could put a point here and here. Let's see. If I put a point here, let's see, that was over 4 up 3. So I would make sure I would go over 4 down 3. Okay, and then let's see, so I might put a point like here. What's that? Now I went over 6 up 7, so I need to make sure I go over 6 and down 7. Alright, so I think that's enough to kind of show what I'm doing here. And so I can go ahead and draw the smooth curve showing the rest of it. So this is the idea. Alright, it's not super easy to draw. Okay, but this graph would have a rotational symmetry around the origin. Just make sure your points that you draw to sort of as you sketch the graph, make sure you pick a few key points and judge that. Make sure you include the origin. And if you went, left 2 and up 1, then go right 2 and down 1. You know what I mean? Reverse it. If you went left 4 and up 3, then go right 4 and down 3. Just do everything backwards, the x value and the y value backwards, and you should be okay. Alright, and we made sure that it had the correct end behavior. So we have our odd symmetry, and on the left it rises, as you can see, and on the right it falls like it's supposed to. Okay, and it has the domain, it has a range of negative infinity to positive infinity. So it fits all the criteria, so that would be a good graph. So there's more than one way to do this. You know, there are probably infinitely many ways to draw this, but this is one handy example. Okay. Number 11. Determine algebraically whether the given function is even, odd, or neither. Okay? Well, I see all the even exponents, so there's a chance that this is going to be even. The way you test to see if something is even, if it's an even function, if I plug in negative x, it should stay the same. Alright? That's how you test for even. So that's what I'm going to do. I see the original function. I'm going to substitute in negative x. And I'm going to see if I get the same function. So if I put in like this, so I've got x to the 4th power. You know what? That's supposed to be an x. I need to change that. It should all be the same variables. Okay, so what was I saying? Yeah, x squared and then plus 6. If I put in negative x for x, let's see if I get the same function. Well, I'm definitely going to get the same function, because if you square a negative thing, it doesn't change. In other words, negative x squared is the same thing as x squared, and that's the same for any even exponent. Negative x to the 4th power is the same thing as x to the 4th power. Negative x to the 6th power is the same thing as x to the 6th power. Alright, I mean, think about it. If I had negative 3 squared, right, that's 9. And that would be the same thing as positive 3 squared, which is also 9. So it doesn't matter. Basically, if you square something, you might as well just erase the negative sign. That works for any even power. So, in other words, this would be the same thing as I could basically just erase these negative signs because they're even power. So this would be the same thing as 9 x to the 4th power minus 4x squared plus 6. Alright? Doing the even power would be the same as getting rid of that negative sign in there. And that brings me right back to the original function. So that means this is even. Oh, guess there's an answer line. Even. Alright, the key is to show that you're plugging in negative x and show that you're getting the same function that you started off with. As far as showing your work, that's the key. Alright, let me clean up my mess. Alright, well, it says write a quadratic equation that has a maximum and zeros at here and here. Well, okay, so we need a quadratic equation, a quadratic function. If we want it to have a maximum, that means it needs to be upside down. Okay, I mean, we know quadratic means, you know, like if it were written out, it would have x squared as the highest exponent. It's a parabola. Quadratic is going to be a parabola. And if it's going to be a maximum, it has to be an upside down parabola, so that it has a high point. And if it's going to be upside down, then it would have to have a negative in the front. Okay, now as far as having these zeros, okay, that means we could get those Xintercept. You know, this is you know, we're looking for a function that would have x-intercepts that are, like 3, 0 and negative 6, 0. Whoa, that's an ugly one. Try that again. And we know that we get these zeros by taking factors and setting them equal to 0. So in other words, we could have gotten this 0 of 3 from a factor of x minus 3. And we could have gotten this 0 of negative 6 from a factor of x plus 6. So if we have this function, then there you go. This would be an equation that would have a maximum because it's upside down, and it would have zeros at 3 and negative 6, because if I set these equal to 0 and solved, I would get 3 and negative 6. So boom, there's the answer. Now I could multiply this out, and I guess I will just for fun, but based on the directions, there's nothing saying I can't leave it in factored form. But if I did want to go ahead and do it, I'd have negative, and this would be x squared, see minus 3, positive 6, that'd be plus 3, and then minus 18. And then if I distributed that negative sign, it would be negative x squared minus 3x plus 18. Alright, so either one of these forms would be a good example. Alright, on with the review questions. Find a plus b. Alright, well, a plus b, we're just going to add these. So negative, maybe I'll just do this off to the side. Negative 31 plus 10 is negative 21. Negative 24 plus 9, and so on. So we get negative 5, 20, and 38 by adding each pair of corresponding elements. So then you just look for which one of these is the answer, and I see that it is C is the one that matches. So the answer to 13 is in fact C. Okay, alright, given this, find negative 2a. Well, that's just taking each of these and multiplying by negative 2, man. Alright, so that should be 6 and 16 and 14 and negative 8. Alright, so where do you see that? 6, 16, 14, negative 8. Oh, look, there it is. So that is D. Alright, remember how you evaluate the determinant. It's going to always be the down diagonal minus the up diagonal. So in this case, down diagonal is 15, up diagonal is 10. So that's just going to be 5. Alright, so that's A. So there you go. Alright, so that was an easy little review. Now for the bonus, the area of a rectangle. We've got this expression for the area of a rectangle. Find the two binomials that could represent the length and width of the rectangle. Justify your answer. Well, the area of a rectangle is length times width. Okay, so if I were to, doesn't this remind you of factoring? So they're telling us that the area is 2x squared minus 7x plus 6. So if we factor that, then we're going to get a binomial times a binomial that could be the length and the width. So 2x squared could be, well, it can only be 2x times x. And then 6. 6 is either going to be 2 times 3 or 1 times 6. I'm going to go with the 2 and 3 first. I definitely won't put 2 here because that would make a common factor with this one, so I will try the 3, 2 option. Now inner, that gives me 3x, and outer, I have 4x. I'm trying to get -7 middle, so I would need a -3x and a -4x, which would give me this. And a negative times a negative is a positive, so that will make +6. So this is the factored form. So with that in mind, then these are the two binomials that that could represent the length and the width. That's it. Also, let me throw in that this expression, 2x minus 3, is always greater than the x minus 2. So this is would best represent the length, and this one would best represent the width. And, you know, for example, if we let x equal 5, then, for example, 2x minus 3 becomes 2 times 5 minus 3. So that's 10 minus 3, which is 7. And then if I look at the x minus 2 expression, then that's 5 minus 2, which is just 3. So this would, of course, be the length, and this would be the width. Okay, so the 2x minus 3 is always bigger, so length, width. Alright, I hope this video has been helpful to you. Please make sure you, if you're studying for recovery or something like that, please make sure that you can do these problems on your own without watching a video or copying off of me. You know what I mean? Watch the video to learn how to do it, but then go back and try to do the problems by yourself and see if you can still do it like the next day. Alright, I will see you on the next video.